All right, chemistry class, welcome back to another installment of our instructional videos, and we are going to continue with looking at acids and bases. And we're going to specifically spend time right now looking at this section here, and we're going to look at 15.1, and we're going to focus on uh, acids and bases and looking at their concentration. Remember we looked at um, a previous chapter and we talked about strong electrolytes, weak electrolytes, and we said strong electrolytes are those that completely dissociate into ions. Well, we're going to have a similar way to define strong acids and strong bases. Strong acids are those that completely ionize, completely dissociate. Okay? Strong bases are those that completely dissociate. Well, again, we would like to measure something to tell us how acidic something is, how basic something is. And that's where this concept of pH comes in. So we're going to be talking about a measurement that allows us to know how acidic or how basic a solution is. Okay? All right, here is a key concept, and I believe I mentioned this in a previous video, but I'm going to mention it again here because it's worth it. This is an important concept here. So point A is that water self-ionizes into hydronium and hydroxide ions. It's kind of a weird concept, but pure water is going to have a small amount of hydronium ions and a small amount of hydroxide ions. It's called self-ionization. Self-ionization. Here's what happens. Let's just imagine that we have two water molecules, and these two water molecules are going to self-ionize. Remember also that water is amphoteric. Amphoteric means it can behave like an acid or a base. It can behave like either. Amphoteric means acid or base behavior. So water is amphoteric. So one water molecule is going to act like an acid, and it is going to donate its proton, H+, to the other water molecule. And that water molecule is going to become H3O+. And the one that lost its proton, its H+, is going to turn into the OH. So if water loses its H+, it's just going to become OH. It lost an H+. If a water gains an H+, it becomes H3O+. So one water molecule is going to act like the acid. How do I know that? Because it is donating the proton, the H+. The other water molecule is going to accept that proton and act like a base. So in the forward direction, one water molecule acts as an acid, donates a proton to the other one acts like a base. In the reverse direction, this hydronium here, to go back to where we started, would have to donate back the H+ to the hydroxide, to the OH negative. So this is your acid in the reverse direction, and this is your base. Remember, there are always pairs. The acid on one side is paired with the base on the other side in the reverse direction. And the base on the forward direction here is paired with the acid in the reverse direction. Okay? This is the self-ionization of water. Now, to what extent does that happen? A very, very, very small extent, but it still happens, and it's still significant. Okay? So you need to write down here that ion concentration right here is an important concept. In pure water at 25 degrees Celsius, what is the concentration of hydronium and hydroxide? Well, the concentration of hydronium ions, when you put it, look here by the way, when you put brackets around the formula, that means concentration, okay? So when I put a bracket around something, it means concentration, okay? So the concentration of hydronium ions is 1 times 10 to the negative 7 molar. And likewise, the hydroxide is going to be exactly the same, because look up here. For every hydronium that is created, a hydroxide is created. They're going to be equal in concentration in pure water. Okay? It also is 1 times 10 to the negative 7. That's really small, but it's still there. Okay, 1 times 10 to the negative 7 means you've got 0.0000007. Oh, sorry, 1. Sorry, not 7. 1. Is that 7 times? 1, 2, 3, 4, 5, 6, 7. Yep. 1 times 10 to the negative 7. That's 0.0000001 moles. Remember what molarity is? Moles per liter. It's really small. Okay? And both hydronium and hydroxide are in the same concentration in pure water. They exist there. Okay? Now, we are going to formulate a way to kind of track the increase and decrease of the hydronium and hydroxide ions. In other words, in pure water, the hydronium ion concentration and the hydroxide ion concentration, if we were to multiply those together, 1 times 10 to the negative 7 multiplied by 1 times 10 to the negative 7 is going to be 1 times 10 to the negative 14. Okay? But if 1 increases, if the hydronium ion concentration goes up because we add something else, then the hydroxide ion concentration is going to have to go down, because these two are in an inverse relationship. As one increases, the other decreases. As one increases, the other increases, the first one decreases. Okay? But their product, as long as it is an aqueous solution, as long as you have a water solution, you can add other things, but as long as it's water, this product is going to equal 1 times 10 to the negative 14 at 25 degrees Celsius. So this right here, ladies and gentlemen, this little formula, we're going to have a constant. This product of the hydronium ion concentration and the hydroxide ion concentration is always going to be equal to this constant, and at 25 degrees Celsius, that constant is 1 times 10 to the negative 14. Okay? 1 times 10 to the negative 14. This constant here, K sub W, a constant for water, is called the ionization constant of water. Okay? Now this is the value, 1 times 10 to the negative 14. That's the value at 25 degrees Celsius. If it's a different temperature, then that K value is going to be different, as you can see over here. And you can see right here that as the temperature increases, this K value is going to go from 10 to the negative 15 up to 10 to the negative 14. So it increases a little bit. Okay, it gets bigger. But at 25 degrees Celsius, this is where we're going to focus. This constant, the ionization constant of water, which is found by taking the product of hydronium ion concentration times the hydroxide ion concentration, is going to be 10 to the negative 14. Okay? Now, if we don't have pure water, by the way, is neutral. Okay? It has the same number of hydronium and hydroxide ions. Pure water is neutral. But if we add something, that is going to change how many hydronium ions in it, like adding an acid, or if we change it by adding a base, that's going to influence the number of hydroxide ions, then this pure water is not going to be neutral anymore. It's going to either be acidic or it's going to be basic. Well, how will we know? It's real easy. Look, here's how you know if something is acidic, by looking at the concentrations. All right? If it's acidic, then that means the hydronium ion concentration is greater than the hydroxide ion concentration. Okay? Remember, this product is a constant for aqueous solutions. So to keep this product a constant, if the hydronium ion concentration goes up because we add something that ionizes into hydronium ions, then the hydroxide ion concentration's got to go down to keep that constant the same of 10 to the negative 14 for a water solution, an aqueous solution. So if hydronium ion is greater than hydroxide ion concentration, it's acidic. If the hydronium ion concentration is less than hydroxide ion concentration, then it's basic. And if they are the same, then it's neutral. Okay? Think of it kind of like a teeter-totter here, a seesaw. All right? If they're balanced, here, right here, if they're balanced, if you have the same concentration of both, then it's a neutral solution. Okay? That means the hydronium ion concentration and the hydroxide ion concentration at 25 degrees Celsius is going to be 10 to the negative 7, and the product is going to be 10 to the negative 14. Okay? Here, if it's acidic, the hydronium ion concentration is much bigger than the hydroxide. That means what? That the hydronium is larger than 10 to the negative 7, and hydroxide is less than 10 to the negative 7. But the product is still 10 to the negative 14. And for basic, it's the hydroxide that's bigger. Okay, the hydroxide now is bigger than 10 to the negative 7, and hydronium is less than 10 to the negative 7. But the product is still 10 to the negative 14. Okay, as one goes up, the other has to go down to make sure the product of their concentration is always 10 to the negative 14. All right? Now, how are we going to actually calculate these concentrations and also calculate something called pH? Let's talk about actually some calculations that we can do. All right? We mentioned before this idea of strong electrolyte solutions. Well, we also have strong acids and strong bases. Strong acids, like these right here, are all ones that completely ionize. When these are put into water, they completely break apart into ions. And these strong bases also completely break apart into water, or completely break apart into ions when you put them in water. Okay? So here's a strong base, sodium hydroxide, completely breaks apart into ions. Notice the one-directional arrow. Everything is going one direction. Okay? So when we have this situation, whatever concentration of sodium hydroxide you have, you're also going to have that same concentration of sodium ions and hydroxide ions. Let me repeat that. For a strong acid or base, whatever the concentration of sodium hydroxide is, or the base or the acid that you're putting in, that also is going to be the concentration of the hydroxide or maybe the hydronium. Okay, we'll look at that situation. So here, if you're told that your concentration of sodium hydroxide that you put into water is 1 times 10 to the negative 2, then you know that also is going to be the concentration of your hydroxide. Because for every 1 sodium hydroxide, there's going to be 1 hydroxide ion. Okay? So if that's the case, if you now know the concentration of hydroxide, now we could say, well, I could now find the concentration of hydronium. This is much bigger. Look, this is much bigger number. 1 times 10 to the negative 2 is much bigger than 10 to the negative 7. So the hydroxide ion concentration has increased significantly. What does that mean for the hydronium? It's got to go down in order to keep the product equal to 10 to the negative 14. So let's actually calculate it. So here, remember this product here of the hydronium concentration and hydroxide concentration is always going to equal 10 to the negative 14. So I can take this constant right here, which is 10 to the negative 14, and divide by now the known concentration of hydroxide ions, which I found up here. And I divide by 10 to the negative 2. When I do that, I get 10 to the negative 12. So that means the hydronium ion concentration is 10 to the negative 12. The hydroxide ion concentration is 10 to the negative 2. Well, 10 to the negative 2 is much bigger than 10 to the negative 12. So the hydroxide ion concentration is greater than 10 to the negative 7, also much bigger than the hydronium ion concentration. And so this is a basic solution. The hydroxide ion concentration is greater than the hydronium. It is basic. It is a basic solution. Okay? Same thing for strong acids. Here we have a strong acid, HCl. If I am told that we have 2 times 10 to the negative 4 molar HCl, and we put that into water, well, now this water, its ionization constant is always 10 to the negative 14, but now it's going to be influenced. One of those ions, either hydronium or hydroxide, are going to go up, and the other one's got to go down. Well, in this case, it is the hydronium that goes up, because an acid donates its H plus to the water, increasing the concentration of hydronium ions. So if this concentration right here, we are told the concentration of HCl is 2 times 10 to the negative 4, well, that means the hydronium ion concentration is going to be that as well. Because for every one of these, HCl, you're going to get one hydronium. So you're increasing the amount of hydronium in your aqueous solution. All right? So now we know when you take this concentration of HCl, 2 times 10 to the negative 4, you're also going to have that concentration of hydronium ions. Now, that is going to boost up the hydronium ion concentration, so the hydroxide's got to go down in order to keep their product the same. All right? So, the hydronium ion concentration, now we know, is 2 times 10 to the negative 4. This hydroxide we don't know, but we do know they're equal to 10 to the negative 14. Okay? Now, was there some hydronium there already in the water? Yes, but it's so small compared to what you're now adding that it really doesn't change the concentration significantly. Okay, it's not a huge increase here. This is what we're focusing on. This is a large amount compared to the hydronium ion concentration that was already there in pure water. So now we take and we solve for the hydroxide ion concentration. You take 10 to the negative 14 divided by the concentration of hydronium, which we have up here, and we find the concentration of hydroxide. Okay? So the hydronium ion concentration is greater than 10 to the negative 7. It's greater than the hydroxide, which is less than 10 to the negative 7. So this is an acidic solution. Okay? An acidic solution. More hydronium than hydroxide. But the product of those two concentrations is still 10 to the negative 14. That's what allows us to solve for one of them knowing the other. Okay? All right. Now, we're going to talk about another measurement here. And this measurement is going to be called pH. Now, I'll tell you why it's called pH in a second. But the concentrations of hydronium and hydroxide ions are going to determine what we call pH, and there's also a pOH. You can see the H here, probably because of hydronium, H+, and the OH because of the hydroxide. All right? So this concept here, we're going to be able to calculate what's called pH and pOH. All right? So we can continue, if we want to, we could continue to express concentration as, 10 to the negative 7, 10 to the negative 14, 2 times 10 to the negative 4. But it'd be nice if we had a simpler number in order to express what the concentration is, okay? And that would help us to kind of simplify this a little bit. So here's what we're going to do, is we're going to come up with what is called the pH and the pOH. It's just a simpler number that still is giving you an indication of the concentration, okay? Let me show you how we calculate pH. pH is simply taking the negative log of the concentration of the hydronium ions. And you may be thinking, oh man, log. I think I learned that, but I'm not quite sure exactly what log is. Well, let's do a quick review of what log means. All right? Log simply means exponent. Log simply means exponent. That's all it means. So if I take the log of 100, and I'm not going to write it all the time, but really this is log, I'm going to put base 10 there. Okay, log of 100 and base 10. What that means is you're asking the question, 10 to what power would give me 100. That's what you're asking. The log is equal to an exponent. Log equals exponent. So you're asking this base right here, whatever the base is, and it's going to be 10 for us, 10 to what power is going to give me this number of 100? Well, obviously the answer is 2. Okay, is 2. And all you need to do on your calculator is you need to punch in a number. You would punch in 100 and then press your LOG button and you would get 2. But what it means is 10 to what power? You're asking, excuse me, you're asking what this exponent is. What would that exponent be to 10? 10 to what power will give you the number that you're trying to find the log of. Okay? So obviously the log of 1,000, well, sorry, log of 1,000, not log equals 1,000. Log of 1,000 is asking 10 to what power will give us 1,000? Well, that's 3. 10 times 10 times 10 is 1,000. Okay? So if I take the log of a concentration, I'm asking 10 to what power gives me that concentration, and then we're going to take the negative of it because these are such small numbers that they're going to give us a negative value, and then we take the negative of it to make it positive. Okay, I'll show you some calculations here in just a second. This, though, notice it's related, pH is directly related to concentration. Okay? This is just another way to tell us concentration, but it gives us a simpler number. Instead of 10 to some power, it gives us a simpler value. Okay? Here, let's look at one. Let's say that you know the concentration of the hydronium ion is 10 to the negative 7. Right there. It's a neutral, it's probably a neutral solution, right? So we take the negative log of 10 to the negative 7. In your calculator, you punch in 10 to the negative 7, take the log of that, and then take the opposite of that value. Well, the log of 10 to the negative 7 is a negative 7. It's right there. And then you take the opposite of it and you get a positive 7. So anytime that you have a neutral solution, the pH is going to be 7 because that means the hydronium ion concentration is 10 to the negative 7. Okay? Let's do a few here. If I have the concentration, and I know the concentration is 10 to the negative 13, and I want to find the pH of that. pH is simply the negative log of that concentration, 10 to the negative 13. Well, the log of 10 to the negative 13 is negative 13, because it's asking 10 to what power gives me 10 to the negative 13? Well, it's negative 13. And then I take the opposite of that, and I get 13. Okay? Now look here for a second. This is a very, very small number. That's tiny, way less than 10 to the negative 7. So your concentration of hydronium ions is very small. Your pH is 13. Okay? If we had a pH when it was of 7, that's neutral. That's neutral right there. Okay? Here we got 13, and we have a very small amount of hydronium. That must mean the hydroxide must be very large. Interesting. Let's look at one where we have 10 to the negative 6. pH is negative log of 10 to the negative 6. Well, the log of 10 to the negative 6 is negative 6, and then I take the opposite of that, and I get 6. So here at a neutral solution it was 7. Here it's 6 when the concentration is greater than 10 to the negative 7. And here it's 13 when the concentration of hydronium is less than 10 to the negative 7. Here's the scale. All right, you can refer to this anytime you need to. Here's our pH. Here's our concentration. Okay? When something is neutral, that means the concentration of the hydronium ions is 10 to the negative 7, as well as the hydroxide ions. Okay? As well as the hydroxide ions. Here, I'm going to put down here also hydroxide ions. Okay? And we'll fill this in as we go. And right up here, I'm going to put something called POH, sorry. Even though we haven't calculated it, I'll show you it's very similar. All right? If it's neutral, that means the hydronium ion concentration is 10 to the negative 7. And the hydroxide ion concentration is also 10 to the negative 7. Okay? As the concentration of hydronium ions increases, look here, increasing acidity, it's going to get larger and larger and larger. It's a negative exponent, it's getting smaller, that means the value is getting larger. This is 10 to the negative 7. If we come all the way up here to 10 to the 0, that's 1. That's 1, okay? 1 molar. In that case, your concentration of the hydroxide would go down as the hydronium goes up. So if it is 10 to the negative 2 for hydronium, then it's going to be 10 to the negative 12 for hydroxide. If it's 10 to the negative 1, it's going to be 10 to the negative 13 for hydroxide. If it's 10 to the 0, it's going to be 10 to the negative 14 for hydroxide. If it's 10 to the negative 5 for hydronium, it's going to be 10 to the negative, you guessed it, they have to always add up to negative 14, these exponents. So it's going to be a negative 9. If we go the other direction, if the hydronium concentration decreases, gets smaller, the hydroxide concentration is going to get bigger. So for 10 to the negative 9 for the concentration of hydronium, then it's going to be 10 to the negative, has to add up to 14, so 5. What if it's 10 to the negative 12 for hydronium? Then it's going to be 10 to the negative 2 for hydroxide. 10 to the negative 14 would mean 10 to the 0 for hydroxide. As one increases, the other decreases. So for pH, remember what we did for pH? pH, if you take the negative log of 10 to the negative 7, you're going to get 7. Okay? Well, for pOH, it also is going to be 7. It's also going to be 7 because they're both going to be in equal concentration. 10 to the negative 8, as the hydronium ion concentration decreases, 10 to the negative 8, the pH is 8, the pOH has to be, this time they're going to add up to 14, so it has to be 6, okay? Here, 10 to the negative 9 has a pH of 9, the pOH is going to be 5. 10 to the negative 10 has a pH of 10, the pOH is going to be 4. These numbers are always going to add up to 14. As we go the other direction, as the pH decreases, if the pH is 6, the pOH is 8. If the pH is 5, pOH is 9, and etc. Okay? So a couple things that we have to observe here. These concentrations are always going to multiply to give me 10 to the negative 14. And the pH and the pOH are always going to add to give me 14. As one goes up, the other has to go down. Okay? Now, quick thing. Oh, by the way, you find the pOH the same way you find pH, but you're just using the concentration of hydroxide. So pOH, this should be pOH here. pOH is the negative log of the hydroxide concentration. Okay? So as I mentioned, the two pH and pOH, which basically stands for power. Power is an exponent. Power of the hydronium concentration plus power of the hydroxide concentration. The two are always going to add up to 14. Okay? Always. And their product is always going to be 10 to the negative 14 of the concentrations. Okay? All right. This little chart kind of sums it up for you. If something is neutral, then your concentrations are going to be equal. And the pH is going to equal the pOH. That's right here in our chart up here. When they're neutral, you've got both pH and pOH are 7, and the concentrations are both 10 to the negative 7. Okay? When it's acidic, you have a higher concentration of hydronium than you do hydroxide. Now, be careful here. If it's acidic, the concentration of hydronium is greater than the concentration of hydroxide. Okay? But pH is going to be low and pOH is going to be high. Let me say that again. pH, when pH is low, below 7, it's acidic. pH, when it's below 7, this is acidic. When it's above 7, this is basic. Okay? If you get confused, looking at pOH and pH together, just focus on pH. When pH is below 7, it is acidic because you have a high concentration of hydronium ions. Remember, it's the negative log. Negative log. That negative log, the negative part, actually kind of makes the pH go down when the concentration goes up. Okay? If pH is greater than 7, then we know it's basic because the concentration of the hydronium is going down and the hydroxide concentration is going up. Okay? And for basic, we know that the hydroxide ion concentration is greater than the hydronium, so that means you're going to have a pH greater than 7, and from like 7 to 14. Or sorry, yeah, 7 to 14. Okay? All right. Now, these two relationships are the only two that you need to know in order to find pH, pOH, concentration of hydronium, and concentration of hydroxide, given just one of them. You need to know these two things right here. Ready? pH plus pOH is always going to equal 14 in an aqueous solution. And the concentration of H plus, or hydronium I should say, and the hydroxide concentration, the product of those is always 10 to the negative 14. Those two relationships right there. Notice there are 4 variables: pH, pOH, hydronium, and hydroxide. If I give you just one of those 4, you should be able to find the other 4, or the other 3. Okay? Let me show you what I mean. All right? Actually, I'm gonna set up a little kind of table for you here. All right? This shows you how to do the calculation and everything, but I'm going to show you a little table to show you exactly how to do this every single time and what to do. Okay? Let's look at, I just want to get some empty space here, okay, to write my descriptor. All right, here we do. Let's do this right here. Okay, here we have pH, pOH, concentration of hydronium ions, and concentration of hydroxide ions. Okay? Now, those are your 4 variables. If I give you just one of those, you should be able to find all of the other 3. Let me show you what I mean. Okay? Let's say, and I'm going to use, what am I going to use? I'm going to use these two relationships. pH plus pOH equals 14, and the hydronium concentration times the hydroxide concentration is equal to 10 to the negative 14. Okay? I'm going to use these two right here. These two relationships will get me wherever I need to go. Okay? So let's say that you are given pH. Let's start here. Let's say you're given pH right there. And I want to find all the other 3. Well, I could go to pOH. All right? pOH means they have to add up to 14. So if I want to go here to pOH, I would just take 14 minus pH, and that would give me pOH. Okay? Well, what if I want to go back the other way? What if I was given pOH and I wanted to find pH? Well, I would just take 14 minus pOH to get my pH. They have to add up to 14. Okay? They have to add up to 14. Now, what if you were given the hydronium ion concentration? What if you're given this one and you want to find the hydroxide? Well, they multiply to give me 10 to the negative 14. So if I want to go from here to here, I would take 10 to the negative 14 and divide by the hydronium ion concentration. Okay? 10 to the negative 14 divided by hydronium would give me hydroxide. If I want to go the other direction, what if I want to go hydroxide to hydronium. Then I would have 10 to the negative 14, and I would divide by hydroxide. Okay? So just knowing that they have to multiply together to give me 10 to the negative 14, I just divide 10 to the negative 14 by the one I know to get the one I don't know. Okay? Now there's one other relationship here, and that is our relationship with pH and pOH. Okay? Remember, pH is negative log of the hydronium concentration. And pOH is negative log of the hydroxide concentration. So now I'm asking, well, what if I want to go between pH and hydronium ion concentration? What if I want to go this way? Or what if I want to go that way? Well, if I know the concentration, okay, if I know this concentration, I take the negative log of that, negative log of the hydronium is going to give me the pH. What if I want to go the other direction? Then I do something called the anti-log, or actually what I do is I take 10 to that power. Okay, I take 10 to the negative pH. This is all you got to do right here. You take 10 to the negative pH, and you will have your concentration. Okay, so one direction you take the negative log. The other direction you take 10 to the negative pH to get your concentration. Okay, same thing over here. If I know the concentration of hydroxide, I would take negative log of that hydroxide, and that would give me the pOH. And this direction, I would take 10 to the negative pOH to give me my concentration of hydroxide. Okay? This chart right here, if you got this chart in your notes, that's all you need in order to find any four or any three, all four of those values. Okay? Let me show you how this works. Okay? So let's say here it says, here's the pH. We are given the pH right here. All right? So we're given this right up here. We're given pH. And we are told the pH is 7.52. Now let's pause for a second. Since the pH is greater than 7, I know that this is basic. This is a basic solution. It has more hydroxide ions than it has hydronium ions. Okay, the concentration of hydroxide ions is greater than the concentration of hydronium ions. Now, what are we going to find? We're going to find the concentration of hydronium ions, hydroxide ions, and I'm going to throw one else in there, another one in here. We're also going to find pOH. Might as well do it while we're here. Okay, so let's go ahead and do this. Let's do this one first. All right, let's do pOH first. I'll call this is A, B, this is going to be D. We're going to find pOH. So let's find pOH first. pOH is what? pOH, to find pOH, we have to take 14 minus pH. I have pH and I want to go to pOH. 14 minus pH. So I'm going to do 14 minus 7.52. That number right there, 14 minus 7.52, you calculate that, that is your pOH. Okay? Now, I want to find the hydronium ion concentration. Okay, so let's do A. Hydronium ion concentration, knowing pH, I have to take 10 to the negative pH. All right? So I would do 10 to the negative pH. So I would do 10, and you got to take out your calculator, and you're going to have to enter 10 and then raise it to the negative 5.2. Okay, raise it to the negative 5.2, and that value is going to be your concentration of hydronium ions. All right? Hydroxide ions, well, you have a choice here. Once we know the hydronium ion concentration, we can find the hydroxide ion concentration. We just have to take 10 to the negative 14, because they always multiply together to give me 10 to the negative 14, and divide by the known hydronium ion concentration. So 10 to the negative 14 divided by this number, whatever this number was. Put that right in there. And whatever you evaluate there is going to be your hydroxide ion concentration. Okay? All right, let's see if we got this right. All right. So here is our hydronium. Knowing pH, 10 to the negative pH, so 10 to the negative 7.52. So on many calculators, you might have to enter the decimal first, 7.52, and then you would make it a negative, and then do second function of 10 to the x. Okay? So that actually is saying 10 to the x, 10 to the negative 5.2. And you should get 3 times 10 to the negative 8. Okay, you might get it as a decimal, but that's 3 times 10 to the negative 8. And then you just take your 10 to the negative 14, which is your constant, and divide by that concentration to get the concentration of hydroxide. Okay? All right, that wraps up 15.1. Now, I'm going to give you lots of practice with the review questions and some more help with finding pH, POH, hydronium concentration, and hydroxide concentration in another video. Okay, so I hope that's helpful. I'll make sure that you have lots of examples to run through. All right, that wraps up pH, POH, hydronium and hydroxide ion concentration, and let me know if you have any questions.